So think about this. What if the next massive leap in technology isn't about making transistors smaller and faster, but about getting rid of them completely? Today, we're going to dive into a pretty mind-bending idea. Computers that don't run on electricity at all, but on pure raw light. For what? A century now. Computation has all been about one thing: the electron. That tiny little particle just zipping through copper wires. It's been the workhorse of our entire digital world. But what if we could swap it out, trade it for something way more elegant and, well, infinitely faster? I'm talking about the photon, the actual particle of light itself. And that, right there, is the whole idea behind optical computing, or sometimes you'll hear it called photonic computing. Instead of pushing electrons around, we'd be manipulating actual waves of light. And the payoff? I mean, it's just staggering. We're talking about a jump in bandwidth and speed that would make today's fastest supercomputers look like ancient relics. Okay, so it's a really cool idea, right? But how in the world do you get light to, well, to think? Let's get into the basics of what it would take to compute at light speed. At its core, it's actually a pretty simple swap, but it has huge implications. Every single computer you've ever used, your phone, your laptop, everything, it all uses electrons flowing through circuits to represent ones and zeros. That's it. Optical computing basically says, let's just throw that whole system out, and instead, we'll use photons, those particles that, travel at the absolute speed limit of the universe. All right, but going from a cool theory to an actual working machine, that is a massive leap. I mean, what would the parts of an optical computer even look like? We're not talking silicon chips and copper wires anymore. We'd be dealing with things like lenses and lasers and special crystals. Look, everything in our digital lives, and I mean everything, from the phone in your pocket to the giant data centers that run the internet, it's all built on one tiny, amazing invention: the transistor. It's just a switch. That's all it is, the most fundamental building block. So if we're going to build an optical computer, we have to start there. We have to reinvent the switch. But this time, it needs to be one that you can flip with a pulse of light, not a jolt of electricity. On the surface, the blueprint for an optical computer would probably look pretty familiar. You'd still need all the key parts, right? A processor, a way to move data, some kind of storage, and of course, a power source. But here is the massive catch. Every single one of those components has to be totally rethought from the ground up to work in a world of photons instead of electrons. Okay, so if this is all so amazing and promising, you might be asking, why are we still using silicon? Well, it turns out that for all of its incredible speed, light has a really big fundamental problem when you try to make it do calculations. And you better believe the skepticism from engineers is real. Think about it. Electronic transistors are an incredibly mature technology. They are cheap, they are super reliable, and they do a ton of complicated stuff in the background to make sure all the signals stay clean and strong. For any kind of optical replacement to even have a chance, it has to match decades and decades of refinement. That's a huge, huge task. And this really gets us to the absolute core of the problem. See, for a computer to compute, its signals have to interact. They have to affect each other. But just, picture this. If you take two flashlights and cross the beams, what happens? Absolutely nothing. They just pass right through one another. And that's the thing with light. Forcing photons to actually talk to each other, to interact, that is the #1 biggest challenge in this whole field. So how do you solve a problem that seems to, defy the very nature of light? Well, you have to get really creative. And as you're about to see, sometimes you have to get just plain weird. Okay, check this out. One of the most brilliant solutions is called time delay computing. Just imagine you build this complicated maze out of optical fibers where every single path has a slightly different length. Then you send in one single pulse of light. It gets to the start of the maze and splits, exploring every single possible route at the exact same time. The solution to your problem isn't calculated. It's revealed by when the light comes out the other side. The computer isn't really thinking in the way we're used to. It's just exploring. It's amazing. And hey, if you thought that was strange, you better brace yourself for this next one. There's a proposed method for solving an incredibly difficult kind of problem that literally just uses office supplies. I'm not kidding. You take a photocopier, you print out every possible answer on its own separate clear transparency sheet. Then you just stack them all up, one on top of the other, and you shine a really bright light through the whole stack. The one tiny spot where light manages to get all the way through, that's your answer. It's this beautiful, almost funny, simple solution to a super complex problem. And look, these are just a couple of examples. Researchers are trying all kinds of wild, unconventional stuff, using different colors of light to stand in for variables, or physically blocking parts of light beams. But what all these strange ideas have in common is what they're trying to solve. They're all aimed at a class of problems called NP-complete. And these things, they're the absolute monsters of computing. They're problems so incredibly hard that even our biggest, baddest supercomputers just give up. They grind to a total halt. And this isn't just about solving some abstract math puzzles. Not at all. Optical computing has a very direct, very powerful use in the single biggest tech revolution happening right now: AI. Right now, companies are building specialized photonic chips. They're designed for one thing: handling the gigantic parallel calculations that AI models need to run. I mean, just imagine it, training the next big AI model not with electricity, but with pure light. So, we've covered the elegant theory, some of the truly bizarre solutions, and the very real-world applications. But where is all this heading? Is optical computing just going to be a niche thing, a cool little side project, or are we maybe, just maybe, seeing the very beginning of a new photonic age? Well, one of the best ways to tell if something is moving past just theory is to follow the money. And there is a lot of money and a lot of talent pouring into this field. We're talking about the big guys like IBM and Microsoft, but we're also seeing a whole new wave of hungry startups, companies like Lightmatter and Xanadu. All of them are placing a huge bet that the future of computing is built on light. Yeah, this is definitely not a science fair project anymore. This is a real, high-stakes race to build what comes next. Which really leaves us with a massive question about the future of technology itself, right? For like 50 years, Moore's law, the idea of shrinking silicon transistors, has been the engine driving everything forward. But that engine, it's starting to sputter. We're hitting the basic physical limits of silicon. So we have to ask, is the next great leap going to come from just making our current tech a little bit smaller? Or is it going to come from embracing something completely new? The future of computing might not just be faster, it might literally be brighter.